Hello students. In the previous lecture 1, we learned how to evaluate a triple integral. Now in this second lecture, uh, we are going to learn the another method of evaluating double or triple integrals by a process called change of variables. In the examples what I considered in the previous lecture, I considered one problem at the end, which is very difficult to evaluate that integral. The integrand is some cumbersome one, and if we apply the integration methods, probably it takes much time to evaluate it. So if we change the domain where we are doing the integration, that means if you change the space where we are doing the integration, we can solve those integrals very easily. That topic we'll consider in this lecture. So far in this unit, we considered from the beginning how to have a double evaluation of double integrals. We learned, and you learned how to find out the limits of the two variables involved in the double integration when the region of integration is given, and evaluation of double integral by change of order of integration. This also you learned, and evaluation of triple integrals that we learned in the previous lecture. Now, how to evaluate double and triple integrals by the change of variables. So, why we need the change of the variables to evaluate the multiple integrals, maybe double integration or a triple integration. Sometimes we come across the evaluation of complicated integrals. Complicated integrals in two ways. One is the integrand may be a complex function to evaluate that integral. That may be the case, or otherwise, even if the integrand is easy, even if the integrand is a simple one, but the region of integration may be a, complex one. It may not be the simple. So in such cases, once we change the variables, then we can solve the problems easily. Almost this kind of thing already you experienced in your intermediate course, like the substitution method. By putting some substitutions, like our example, if you have square root of a square minus x square between 0 to a, by substituting x is equal to a sine theta, you are able to solve it very easily. So that kind of simplifications um, give us very easy way of evaluating the integrals. So in such situations, the change of coordinate system by proper substitution, that means the transformation if you make, that facilitate to replace these integrals by the integrals that are easier to evaluate. The transformations may change the region of integration or the integrand or both so as to evaluate the integrals easily. Just to give you one idea, I'll suppose you what actually the transformation means. Suppose you in the XY plane, you have say a quad a square region, some region you have with these vertices 0, 0, 1 by root 2, 1 by root 2, 0, comma root 2, minus 1 by root 2, 1 by root 2. These are the vertices of a quadrilateral. And see here, yeah, you have a quadrilateral uh, with the vertices 0, 0, that is 1, and another one is 1 by root 2, and another 1 by root 2. This is the point, and minus 1 by root 2, 1 by root 2 is 1, and 0 comma root 2 is another one. So this is minus 1 by root 2, 1 by root 2, and this point is 0 comma root 2. So you have some quadrilateral. Uh, if you want to evaluate a double integral over this region, then you cannot do it directly by integrating first with respect to y, next with respect to the reason being here up to you have to divide that into two parts, R1 and R2. This kind of problems already you discussed in the you learned in the concept called evaluation of double integrals. But if you make this region of integration, if you make this region of integration as a simple one instead of this R, it takes some other form, then it will be easy for you to solve that problem easily. See here, if I take this substitution, u is equal to x minus y by root 2 and v is x plus y by root 2, then let us see what happens to this transformation. So this is the transformation what I am considering is u is x minus y by root 2 and v is x plus y by root 2. That means from this xy plane, I am going to some other plane called uv plane. This is u, this is v. Now the point 0 in the xy is the point 1 point. This is uv is another point. So when I take xy as the point 0 0, according to this transformation, u is equal to x minus y by root 2, v is equal to x plus y by root 2. If I substitute here, u value will be 0, v value also is 0. But if I take the another point, say 1 by root 2, 1 by root 2, then u is x minus y by root 2, 1 by root 2 minus 1 by root 2, u value is 0 and v value is I have to add these two and I have to divide it by root 2. If I add these two, 1 by root 2 plus 1 by root 2 is 2 by root 2, 2 by root 2 means that is root 2, root 2 by root 2 is 1. So that is 0, 1. Similarly, if I have another point, minus 1 by root 2, of course the 0 root 2 is another one what I have there. This is 0, this is root 2. If I take 0 root 2, x minus y by root 2, so that u value will be minus 1, 0 minus root 2 by root 2, and x plus root 2 by root 2, that will be 1 minus 1, 1 is the other point. And one more point I have, that is minus 1 by root 2, comma 1 by root 2. In this case, u will be difference of these two, minus 1 by root 2 minus 1 minus root 2 by root 2, that is minus root 2 by root 2, this will be minus 1. And if I add these two, this will be 0. So the points will be transformed to these points in the UV plane. So, okay, in this UV plane, let us see how that figure changes. So 0, 0 has changed to 0, 0 in the UV plane. This is U, this is V. And 1 by root 2, 1 by root 2 is a point which is here 0, 1. And 0 root 2, this is minus 1, 1. And minus 1 by root 2, this is minus 1, 0. So these are the 4 points. That region, by this transformation, you can easily observe evaluation of an integral over this region R. I am calling this region as R dash. Evaluation of the integral over this region R and over this region R dash, if you observe, it is very evident that evaluation of the double integral over this region is very easy. So this transformation has given us, as otherwise this transformation has transformed this region to this region very easily, to a simple region. Therefore, we can evaluate the integral very easily. Okay, this is what a transformation is. Now we are going to learn is the double integral what next the what is that we are going to learn is the double integral over this region R of a function f of xy uh, is equal to double integral over this region R dash. What is the integrand and what could be the integrand? So here this is the transformation what we have taken u and v. So from this transformation I can as well find out x. I can find y x in terms of uv and as well I can find out y also in terms of uv. In place of these x and y, if I write the functions in terms of uv, this you will get some other function capital F of uv, you will get this. What happens to this dx dy? Does it become du dv or not? So how these two will be equal? This is what we are going to learn in this particular chart, lecture. Okay, so let us see here. Now for a double integral, if you take, suppose R is the region of integration in the xy plane, and we need to evaluate this. Suppose I consider a transformation u is equal to g of xy and v is h of xy. Some transformation, so from xy plane to uv plane, I am changing. I am taking a transformation using this. In the previous example, this g of xy is x minus y by root 2, h of xy is x plus y by root 2. This is the transformation we have to have taken. And this transformation should be such a way that I think you learn what actually the Jacobian is in your first semester. So if I find the Jacobian of UV with respect to XY, if I find out this, that should be non-zero and that Jacobian should exist. Jacobian, I think, is determinant. Determinant is maybe zero or non-zero, but this transformation should have this property. See, because if I want to have okay, I'll give you one more. In the previous explanation, from this transformation, I am finding the values of x and I am finding the values of y in terms of uv. So to have that inverse transformation, what I need is this Jacobian should be non-zero. Because in the Jacobians you learned Jacobian of xy with respect to uv. Here it is Jacobian of uv with respect to xy. Jacobian of xy with respect to uv is 1 by Jacobian of uv with respect to xy. Product of those two is always 1. That property already you learned. So because of this non-zeroness, the inverse transformation. From this, I can write x in terms of uv and y also in terms of uv. Thereby, I can this value also will be non-zero. Jacobian of xy with respect to uv is also not equal to 0 because this is non-zero, this is also non-zero. So let this transformation maps the region in the xy plane, the region R, xy plane. It is in the UV plane, the transformed region I am representing with E. In this previous, in the just now I explained with R dash. In place of R dash, I am using the symbol E. Okay, so that is what we have. See, here you have some region in the xy plane and the transformation. By the transformation, suppose you have some region here, R is the region, and here you are getting some other region, say I'm calling this as E. So if I take one point here, correspondingly, I can have one more point here. The transformation u is some u is equal to function of xy, v is equal to another function of xy is given. So using this transformation, a point here will be transformed to a point here. Similarly, if I take very small area of rectangular area of dimensions delta x or dx and dy, this area will be dx dy. So automatically every point here, here also you will have some quadrilateral. This dx dy will be transformed to some very another elementary area. I am calling it as du dv. So it need not be this because this is a rectangle. It need not be a rectangle. Maybe definitely it is a I can say quadrilateral. Now the thing is dx dy and du dv both are same or not? Here what happens is this du dv will be equal to Jacobian of xy with respect to uv into dx dy. So the proof for this is something beyond the scope of the syllabus. I am not giving it here, but still, if anybody is much more interested to learn the things, go through the books. If you find anywhere else, fine. If you don't get the answer for it, you can consult me. I'll definitely let you know how you get it. Okay. Okay. So this dx dy. Okay, this is this constant of integration. This dx dy will be Jacobian of xy with respect to uv times du dv. So double integral or f of x by dx dy will be equal to, in place of x, you need to write the function g of xy. In place of y, you will write some h, so that this entire one will be a function of uv. And Jacobian of xy with respect to uv is also will be in terms of uv. So this entire one is a function of uv and du dv. So region in xy plane, region in uv plane is r and e respectively. So whatever region you get in the uv plane, on that region we need to find the integrals. Here on this region you need to find out the limits of the integration. So this is what the change of variables is. Similarly, in the triple integral, the same way, if you have some region in space, in the xyz space, and we need to evaluate this triple integral over this region R, and consider this transformation u, v, w, because you have three variables, you'll have a u, v, w space. In that u, v, w space, this transformation is such that Jacobian of u, v, w with respect to xyz exists. Of course, existence anyway, it always exists. Existence, the reason for writing existence is dou u by dou x, dou u by dou y, dou u by dou z will be there as the elements of the determinant. So u should be differentiable with respect to x, y, and z. That's what actually that means. Existence is not for existence of the determinant, existence of the partial derivatives, because Jacobians involve in the Jacobian, the elements are partial derivatives of u with respect to x, y, z. That means u should be differentiable, v should be differentiable, w should be differentiable. And if we evaluate that determinant, that should be non-zero. If you take such a transformation, automatically you will have the inverse transformation. X is equal to in terms of uvw, y in terms of uvw, z also in terms of uvw will exist. That exists. And this transformation actually maps, or it transforms the region R in the XYZ plane to a region E in the UVW plane. You will, instead of integrating over the region R, we integrate over E, because this transformation makes that either the integrand or the region simple to evaluate. So this is, and here also whatever function you have, in place of xyz we replace this, and you will get, it will be a function of uvw. If you have dx dy dz, this will become the Jacobian times du dv dw. Okay, that is what we have. So elementary volume, as I mentioned previously, here also, if you have in the three-dimensional space, you have some region R. Similarly, in the UVW, here also you will have some other region E, and this is the transformation. And if you have some elementary volume, elementary of dx, dy, dz, and this elementary volume will become here some elementary volume here also, and this is du, dv, dw. The volume of this and the volume of this, the relation is this dx, dy, dz. The volume of this is some constant times that constant is Jacobian of xyz with respect to uvw du, dv, dw. So in the last semester you learned Jacobian. So the one application of Jacobian is this. Once you find the Jacobian of xyz with respect to uvw, this will give you how many times the volume, elementary volume here in xyz space, and the in the uvw space you will have another elementary volume. The ratio of the volumes is the Jacobian. Dx, dy, dz by du, dv, dw is this. That is one application of the Jacobians. Okay, this is how we'll evaluate the double integrals. So this, in place of x, y, z, you write this function g. In place of y, you will write h. In place of z, you will write k, and this dx dy dz will become Jacobian of xyz with respect to uvw du dv dw. You are converting from xyz to uvw, therefore Jacobian is to be evaluated from xyz with respect to uvw. Okay, right. Now, to understand this concept easily, I am solving some problems here. Evaluate integral 0 to 1, integral y by 2 to y by 2 plus 2, 2x minus y dx dy. And this, by using this, you need to make the substitution u is equal to 2x minus y and v is equal to y. This is what the problem is. Okay, let us evaluate this. Yeah. So the integral what he has given is 0 to 1, 0 to not 0, it is y by 2 to y by 2 plus 2 and 2x minus y dx. Of course, this we need not say because these are functions of y. It has limits for x, therefore with respect to x first, next with respect to y. This is the problem. Okay, is it necessary to evaluate this particular problem by the change of variables? Not necessary. Of course, for this particular problem, we can as well find out the integration. You can integrate with respect to x first, therefore integral 2x is x square by 2. You will substitute the limits, integral y is xy is the integral. Substitute the limits, after that integrate y, you will get the answer. No problem at all. But we are learning the uh, change of variable concept. And the same problem, suppose you are asked to evaluate by change of order of integration. By change of order of integration is asked, not change of variable, change of order of integration. Then we need to write down the rough sketch. X is equal to y by 2 means x is equal to y by 2 means 2x minus y equal to jar y is equal to 2x, a line passing through the origin. Another one is x is equal to y by 2 plus 2. X is equal to y by 2 plus 2 means it is 2x minus y is equal to 4. So you have another line parallel to this. And y, these are the x is equal to y by 2, x is equal to y by 2 plus 2. And y varies from y is equal to 0 to y is equal to 1. So this is your region of integration. If you are asked to solve this by change of order of integration, then you need to divide that into three regions. You have to evaluate integral over this region, and also this region. It's a very difficult one. So if I change this region into a simplest one, I can solve it very easily. For that, this change of variables will help me. What is the transformation you have taken? So if I make these two lines as some parallel lines to the variables, that will be easy. There, that is why I am taking this 2x minus y as one variable. U is equal to 2x minus y. This is one substitution what I made, and another substitution is v is equal to y. If I make this substitution, what happens to the region of, first of all, because this is the transformation, for solving this problem by change of variables, I need x and y in terms of uv. U and v in terms of xy are known. Now find out x from it. X is u plus y means v by 2. And what is y? Y is v. X in terms of uv, y also in terms of uv I have. So for solving, anyway, I need this Jacobian of xy with respect to uv for solving the problem. So I will calculate it. Dou x by dou u, that is half. Dou x by dou v, that is another half. dou y by dou u, that is 0, dou y by dou v, that is 1, and if I evaluate, this is half. Even for some cases, even if you get a negative value here, but while using it, we need to take the only positive value for it. Of course, here half we get. This is Jacobian. Now let us see to what region it is changed. Now you have one line here. This line is 2x minus y is equal to 0. What that 2x minus y equal to 0 becomes? 2x minus y equal to 0 implies the transformation is 2x minus y is used as u. Therefore, that is u is equal to 0. And what is for this domain, what is other boundary? Other boundary is this. What is this line? 2x minus y is equal to 4. 2x minus y is equal to 4 means in uv coordinates it is equivalent to u is equal to 4. And what is the other one? This is y is equal to 0 is another boundary. Y is equal to 0 means here the transformation is v is equal to 0. And y is equal to 1 is another boundary, therefore v is equal to 1 is. So in the uv plane, what are the, how that lines becomes? 1 becomes u is equal to 0, this is u axis, this is v axis, then because this is u axis, this equation is u is equal to 0, this is v equal to 0, u equal to 0, u is equal to 4 is another line, v equal to 0 and v equal to 1 is another line. So this figure in the xy plane, we have a region like this, this has transformed to this. Clearly, this is very easiest. So this is the region E, this is the region R. He is asking us to evaluate double integral over R. Integrand is 2x minus y dx dy. This is what he asked us to evaluate. Now I am evaluating it by this. In double, this is equivalent to double integral over E 2x minus y according to the transformation. 2x minus y is my u. Therefore, this is u. The dx dy. Dx dy is Jacobian times. Jacobian is, here I calculated the Jacobian. I got 1 by 2. So here we got 1 by 2. So that Jacobian times du dv. So now in this region E, how to take the limits? Very easy. Because it is a rectangle, u is equal to 0 to 4. These are the limits for u, and v is equal to 0 to 1, and u by 2 du dv. So instead of u by 2 integral is 1 by 2 is anyway constant. Integral u is u square by 2. If I substitute the limits for 4 square, that is 16 by 2, that is 8. 8 by 2 dv between the limits 0 to 1. So integral 8 by 2 is 4. 4 v, if I substitute the limit, that is 4 into 1, that is 4. The integral value is 4. Even if you integrate this by usual method, you will get the same. So this is example 1. The same 4 you will get. Even by change of order of integration, if you split it into 3 parts, then also you will get the value equal to 1. So this is the first problem. Coming to the example 2. Here in this example 1, the limits are given to you directly. But in the example 2, we need to find out the double integral over dy dx dy, where d is the dy dx or dx dy, anything you can write because limits are not given here. That will be where d is the region bounded by y square is equal to 4x plus 4 and y square is equal to 4 minus 4x by the transformation x is equal to u square minus v square and y is equal to 2uv. A beautiful example. This clearly explains you the necessity of using this change of variables. So in this example, he has given a region bounded by two curves. What are these two curves? Y square is equal to 4x plus 4. I think you know y square is equal to ax plus b represents a parabola. Because y square is there, the axis of that parabola is x-axis. Where it cuts the y-axis it cuts at y square is equal to 4. It cuts also at y square is equal to 4. That means y is plus or minus 2. Where it cuts the x-axis, this cuts the x-axis at minus 1. It cuts the x-axis at plus 1. Okay. Now this is 1, this is minus 1. You have one parabola like this, and you have another parabola. Yeah. This is minus 2, so 0 minus 2 is this. This point is 0 comma 2. This is 1 0. This is 0 1. I need to evaluate this double integral. This is my region R. The double integral. What is the integrand he has given? It is integrand is, let us see, what is the integrand? Y. Integrand is y. In double integral over y, we need to do it. Double integral over r y dx dy. This we need to evaluate. Without using change of variables, if you want to do it straight away, how do you find the limits? Because this equation is y square is equal to 4 plus 4x. From this, the x value is y square minus 4 by 4. This parabola is y square is equal to, sorry, this is 4 minus 4x. This is y square is equal to 4 plus 4x. So from this, the x value, if I calculate, it is y square minus 4 by 4, and it is y square 4 minus y square by 4, and this is from minus 2 to 2. These are the limits you need to evaluate this integral. Again, while doing that integration, you feel some kind of difficulty. So let us change this region of integration. I'll change this region of integration to another region in the UV plane by taking the transformation x is equal to, this is the transformation what I use, x is u square minus v square and y is 2uv. If I take this substitution, uh, from this I need to find out what u is, what v is, and I need to evaluate the values of u and v also. Okay, let us first find out what happens to this boundary. That boundary is y square is equal to 4 plus 4x. In UV plane, what happens to this? Y square is 4 u square v square is equal to 4 plus 4x is 4u square minus 4v square. 4 I can cancel, and if I bring everything on one side, u square v square, and here it is minus u square plus v square and minus 1 is equal to 0. So for after cancellation 4. In these two, I can take u square common, u square plus 1 if I take common, it will be v square minus 1. In these two, if I take u square, it is v square minus 1, here also is square. So u square plus 1 will never be 0 because u square positive. Therefore, only possibility is v is equal to 1, v square is equal to 1, that means v is plus or minus 1. Therefore, this parabola, this parabola in UV plane has become y is equal to 1 and y is equal to minus 1. This is, sorry, not y, v equal to minus 1 and v is equal to 1. Similarly, what happens to the right side? The another curve is y square is equal to 4 minus 4x. So if I simplify this, y square is 4 u square v square is equal to 4 minus 4x 4u square plus 4v square. Again cancel that 4, bring everything on one side. U square v square plus u square minus v square minus 1 is 0. In these two I can take u square common. If I take u square common, it is u square minus 1 into v square plus 1 is 0. So from this, anyway, this is not never become 0. Only this will become 0. U square minus 1 is 0. That is u is plus or minus 1. Therefore, the two curves, what you have on this side, they have become lines. The two curves have converted to the lines. A region here has become a rectangle. So what are this? V equal to 1, V equal to minus 1, V equal to 1, U is equal to minus 1, U is equal to 1. This is my region E, whereas this is my region R. This is y-axis, this is x-axis. Now, double integral over the region R, y dx dy, if you want to evaluate, this is equal to double integral over E. This y means, what is the transformation you have taken? Y is 2uv. Therefore, this y becomes 2uv and dx dy becomes Jacobian times. So I need to have the Jacobian of xy with respect to uv. What is that Jacobian? Dou x by dou u. X is u square minus v square. This is the transformation he has given. Then dou x by dou u is 2u. Dou x by dou v is minus 2v. Another transformation is y is equal to 2uv and dou y by dou u. Dou y by dou u is 2v and dou y by dou v is 2u. So that it will be 4 times u square plus v square. This is my Jacobian. So that Jacobian times 4 times u square plus v square du dv. So I need to evaluate this integral. Jacobian, now I will evaluate this Jacobian integral here. What are the limits? Limits are very easy. This is the region E. In this region, limits are minus 1 to 1 and also this is minus 1 to 1. What is the integrand? 4 to 8, that 8 can be taken out. Integral minus 1 to 1. And if I multiply this, u cube into v, u cube into v, with respect to u, I have to evaluate. Limits are minus 1 to 1. So u cube is an odd function. Therefore, u cube into v will become 0. And another term is u v cube, v square, u v square. Again, that integral value is also 0. Integral u v square, u v cube. U v cube, u is a constant, therefore that is also 0. So 4 u square plus v square, this is the integrand, and this is integral minus 1 to 1, integral minus 1 to 1, u cube v plus u v cube du dv. First, I need to integrate with respect to u. So this u cube is an odd function. Therefore, that integral value is 0. Here also u is an odd function. That integral value is 0. So this integral value is 0. And okay. coming to the next problem. Yeah. So in these two examples where I have given, the transformation made that region of integration simple. If you observe this here, e power y by x plus y double integral over d, where d is the region. Region is a simple, very, very easy. X is 0, y is 0, x plus y is equal to 1. A simple triangular region he has given. But such for simple regions, no need to do the change of variables. But here the difficulty is the integrand. So e power y by x plus y, this if I want to do the integration with respect, you can integrate e power x, you can integrate e power y, but integration of e power 1 by x is not easy. E power 1 by y is also integration of e power 1 by y is also not easy to evaluate. So that x and y is there in the denominator. Whether you integrate first with respect to x or y, in any case, this will make you trouble to solve this. So make this as one variable. That is what he did here. X plus y, he made it as u, and in numerator y he has made uv. Uv by u, therefore it will become v. That is the idea. The cumbersome integrand is some difficult. This integrand is difficult to evaluate. Integrand is something difficult for the getting integration. Therefore, I am making that integrand simple one. This is another advantage of this change of variables. So let us solve this example 3 also. Example 3. So what we have is integral e power y by x plus y dx dy. Some reason he has given as d, that d is x is 0, this is y is 0, x is 0, x plus y is equal to 1. Now this is the substitution what I am making, that u is x plus y and y is uv. From this if I calculate x is equal to u minus y means uv, and y is uv only. Okay. So if I take this substitution, then what I will find out the Jacobian. Jacobian of xy with respect to uv. Dou x by dou u is 1 minus v, dou x by dou v is minus u, dou y by dou u is v, dou y by dou v is u. This is u minus uv, this is minus or minus plus uv. Ultimately, Jacobian value is u. So, and how this region of integration changes. If x plus y is equal to 1 is 1, well, then it will become u is equal to 1. And another is x is 0. X is 0 means x is represented as u minus uv equal to 0. This means u into 1 minus v equal to 0. This means u is equal to 0 or 1 minus v equal to 0 or v equal to 1. 1 minus v equal to 0 means v equal to 1. Similarly, y is equal to 0. Y means uv equal to 0. That means u is equal to 0 or v equal to 0. Therefore, the boundaries are u0, v0, v1, u0 and u1. So that triangle region has become a square. One is, this is u axis, this is v axis, this is u equal to 0 is one, v equal to 0 is another one, v equal to 1 is another one, and u is equal to 1 is another. So it's a square. This is the region E. Therefore, double integral over R, that integrand is e power y by x plus y dx dy. This is becoming double integral over e power y means uv by x plus y is u, dx dy becomes Jacobian times, the Jacobian is, I calculated the Jacobian here and I got it as u u du dv. Now I will take the limits as 0 to 1, 0 to 1, e power v into u du dv. So this is integral 0 to 1, e power v is constant, integral u is u square by 2, and after that if I substitute the limits 1 by 2 dv, this is 1 by 2 into integral e power v is e power v only. If I substitute the limits 0 and 1, upper limit will be e minus 1. So the integrand, this value is e double integral over r e power y by x plus y dx dy is half of e minus 1. This is uh, the example 3. So one more example. Of course, this is so far we did for two variables, and now I am doing it for three variables. 0 to 3 and 0 to 4, x is equal to y by 2, x is equal to y by 2 plus 1, 1/6 of 6x minus 3y plus 2z. By changing the variables, this 2u is equal to 2x minus y, 2v equal to y, 3w is equal to z. Yeah, this is example 4. Integral 0 to 3, 0 to 4, x is equal to y by 2 to y by 2 plus 1, 1/6 of 6x minus 3y plus 2z dx dy dz. These are the limits for x, dx, dy, dz. Here he has written x, therefore first of all with respect to x, dy, these are the limits for y, these are the limits for z. Now what is the transformation he has given? 2x minus y is equal to 2u. 2x minus y by 2 is equal to u. And similarly, v equal to y by 2, or y is equal to 2v, and z is equal to 3w. From this, I will calculate x. 2x is equal to 2u plus y. Y means 2v by 2. This is simply u plus v. Y is 2v. W is, what is W? Is, sorry, I need to find out Z. Z is 3w. Because I know these three, I'll calculate the Jacobian of xyz with respect to uvw. Dou x by dou u is 1, dou x by dou y is 1, dou x by dou w is 0, and similarly for this is 0 to 0, 0, 0, 3, because it's upper triangular matrix. Product of the principal diagonal is the determinant, therefore it is 6. 6 is the Jacobian value. Now, what happens to this given integral 0 to 3, 0 to 4, y by 2 to y by 2 plus 1. Once integrand is 1/6 of 6x minus 3y. If I take 3 common, it will be 2x minus y, 2x minus y by 3 by 6, that is 2. Here I have taken 3 common, 3 by 6 is 2. 2z by 6, that means z by 3, plus z by 3 dx dy dz. This is equal to integral, triple integral. Now, before I need to find out what actually the region. Here, y by 2. What is x is equal to y by 2? According to y by 2 is v. So, x is equal to y by 2 is the limit. That means it is 2x minus y equal to 0. But what is 2x minus y? 2x minus y by 2 he is given as 2u. It means 2u is 0. Once 2u is 0, u is 0. So one limit has been. Another one is x is equal to y by 2 plus 1. And if I simplify this, this is 2x minus y is equal to 2. 2x minus y is 2u is equal to 2. That means u is equal to 1. So another limit is u equal to 0, u equal to 1. These are the y is equal to 0. Y means 2v. 2v is 0. That means v is 0. Y is equal to 4. Another limit 0 to 4. Y is equal to 0 to 4. 2v equal to 4. That means v equal to 2. Another one is z is equal to 0. Z is 3w. 3w is 0. That means w is 0. This is v0 is 1. V is equal to 2. W is equal to 0. Similarly, z is equal to 3 is there. 3w is equal to 3. That means w is equal to 1. Therefore, the region of integration now it is, this is, so uvw, u is equal to 0. This is u equal to 0. This is u is equal to 1 because this is u axis, this is v axis, and this is w axis. And next is v equal to 0, w is equal to 0, and w is equal to 1. The front projected one, that is v equal to 1, the backside one, that is v equal to 0. So this is my region E. So triple integral over this region E we need to evaluate. But the u limits are 0 to 1, v limits are also 0 to 1, w limits are, no, w limits are 0 to 1, v limits are 0 to 2. This is v is equal to 2. V limits are 0 to 2. U, V, W limits are also 0 to 1. And the integrand is, what is the integrand here? 2x minus y. 2x minus y, what is the substitution? Transformation is 2x minus y by 2 is u. Here I have 2x minus y by 2. Therefore, the first one is u plus, next I have z by 3. Z is 3w. So z by 3 is w. U plus w. These are the limits for u. Therefore, du, dv, dw. So first of all, I need to do the integration with respect to u. Integral u is u square by 2. If I substitute the limits, it is half. Integral w is wu. If I substitute the limits 0 and 1, it is w, dv, dw. Again, integral of 1 by 2 with respect to is 1 by 2 into v. If I substitute the limits 1 by 2 into 2, w into v, that is 2w, between the limits 0 to 1, dw. Integral 1 is w. If I substitute the limits 1, 2w is w square. If I substitute the limits again 1, ultimately it is 2. So the integral for that is 2. So this problem also I did. So example for practice I have given here. Few more examples I'll mail you a list of problems in this unit, as generally we'll give it as an assignment. Instead of that, we'll do it here. Okay. So this lecture is change. Today I have given you how to change the variables. Now in these examples, you observe that you are changing from xy plane to uh, another plane, uv plane, or the space uv xyz space to uvw space. Space is changed. Now we are changing another change of variables to polar coordinates. Particularly, if I take the particular case, if I change the Cartesian coordinates to polar coordinates, the main important point is in the examples in this lecture, what in this lecture 2, you observed that once you apply a transformation, the region of integration is also changing. But once you change from Cartesian coordinates to polar coordinates, the region of integration won't change, but only thing is how we look at it, and all those things we'll discuss in this particular in the next lecture. The change of variables to polar coordinates. In two dimensions, we have one polar coordinates. In three dimensions, we have spherical polar coordinates and cylindrical polar coordinates. We discuss all those things in the next lecture.